Yes, friends, is the Excel screen visible? Common?
Yes, sir.
Is- Yeah, okay. So good afternoon, everyone. So in today's class, we'll be discussing about the design of doubly reinforced beam. Here I've adopted a very easy approach so that you'll be able to understand the things in a short, simple, and a easy way. So here we have the given data. In the given data, we have bending moment given as 150. The beam section is 230 by 450. The clear cover adopted is 30 mm. The bar diameter we have here is 20 and 16. So generally what happens is in a doubly reinforced beam, we have two reinforcement. One is the tension reinforcement, other is the compression reinforcement. So tension reinforcement will be higher. So we adopt a bigger bar diameter. Anyhow, we can change it as per the need. As we are using Excel sheet, it is not that difficult. We can change it. And we have one more bar diameter given as 16, which we can generally use for compression reinforcement. So grade of the steel given is Fe415 and grade of the concrete mentioned is M20. So it's very much similar to the first experiment which we have done as singly reinforced beam. So some modifications we'll do from the exact method what we adopted while solving the example in the notebook so that the things become easy. So now let us go to the worksheet. So this is your worksheet. I have divided the worksheet into two parts. So one is representing the actual solution what we want, and second one is the explanation. This is the explanation part is for your understanding. This explanation part is for your understanding, and this is the main sheet which you have to do. So I request you all, you can keep the mobile phones horizontally if you want, so that you'll get a better view. Entire page will be covered. So in the last class itself, we have seen how to connect the given data to the worksheet. In similar way, I have connected the given data to the worksheet so that any changes made in the given data directly they'll refer in the worksheet. So how we have to do that is, once again I'll repeat. Actually, we have done the same thing in the last lab also, but still for your information and knowledge, once again I'll repeat it. So in the given data, the moment is 150. So I want the same value to be reflected in the worksheet. Okay, here in the given data, the moment is 150. I want the same value to be reflected in the worksheet. So what I'll do is I'll go to the worksheet in the moment column. On the working toolbar, I'll press equal to. I'll come back to the given data sheet. Okay, I'll come back to the given data sheet. Click on this 150. Now see here, F5 means F column, fifth row. We have got this 150 value. Press enter. Directly in your solution sheet or the worksheet, you have this value as 150. So if you make any changes, instead of 150, I'll make it 170. Press the enter button. Directly when you go to the worksheet, the value is already changed. Okay, see here the value is already changed. That is how we have to link the given data sheet with the worksheet. So let me make the change as it is 150. Automatically it has changed there. So similarly from here I have taken all the given data into the data sheet, connecting from given data only, so that any changes if I make here, automatically I'll get the changed solution. Now this is the effective depth calculation. How we get the effective depth is, now this side I have mentioned the formulas also, because these are easy formulas, not a big deal. So this is your step number 8 for step number 8, here I have given the formula. This is the actual formula which we are using, and this is the input in the Excel sheet. Okay, this is the actual formula which you are using, and this is the input in the Excel sheet. So how you get effective depth is total depth minus D dash. D dash is the cover. Now, as it is a singly reinforced beam, as only one cover is given, we'll assume that this cover is both for compression region as well as tension region. So effective depth, we get it as 450 is the given depth minus, when we do 30, which is the cover, we get an effective depth of 420. So how to write this in the formula? How we get this 420 is D7. Now what is D7? See this column. In this column, D column, 7th row. Okay, this is 450. So this is capital D. From this, we are minusing the cover, which is 30. So we get an effective depth of 420. The formula is mentioned here, step 8. Okay, step 8 formula is mentioned here. D7 cell minus D9 cell. So when you are practicing, just you have to refer these values. See that your columns and rows match this. So only I have sent you all Excel sheet also I have sent, as well as PDF also I have sent you all. Now next, we come to limiting depth of neutral axis. Now again, this is the same as we had done in the previous lab. XU limit for this step number 9. We can refer the table here. This is step number 9, and for the step number 9 corresponding table is there, which we can refer. This table we have used in RCC subject. So how we get XU limit is, depending on the grade of steel, the values change: 0.53D, 0.48D, 0.46D. Or you can enter this formula itself here, but if you change the grade of steel, you have to manually again change the formula. So I have connected it with the table only. Now once again I'll repeat the same thing which I told you all in the previous class. Here the formula is written. When you are doing the experiment, okay, when you are practicing on your own, here I have written this formula. Okay, here I have written this formula so that you all can do that properly. See here the formula is there, which you have to refer. Okay, this red colored mark. It gives you the if condition. What does it say? If D13 is 250. Now see here, which is the D13 column? Yes, it is the FY column. So if D13 is 250, value taken will be 0.53. Now see this brackets and commas as it is, you have to keep. Now if D13, that is FY value is 415, you take 0.48, and if FY value is 500, you take 0.46, and anything what you take, you multiply by D. Now D is representing D17 cell. So this is D, and when you see the 17th cell, D17, that is 420 value, is nothing but the effective depth. This is how you connect the cells. So you'll get the value of XU limit. Then once you get the value of XU limit, go to the limiting moment value, that is MU limit. Again, we have the formula based on grade of steel, and MU limit formulas are mentioned here. So it is clearly written. This is step number 10. This is step number 10. And for this, this is the corresponding step number 10 table. Okay. So again, which formula I have used here? If condition I have used. If grade is 250, adopt 0.148. If grade is 415, adopt 0.138. If grade is 500, adopt 0.133. So it is clearly mentioned which has to be, what has to be taken as per the grade. Okay, so using that, I get the value of maximum MU limit as 111.98. Get the value as 111.98. So when you refer the step number 10, here come to the step number 10, and here you'll be having this formula. Okay, so this is the formula which you'll use to do this step. So I've highlighted that in red color just now, so that becomes easy. So by this we get the limiting value of moment of resistance as 111. Now what you observe here is the limiting moment is 111.98, whereas the given moment is 150. So either it will be a over reinforced section, If we are designing a singly reinforced beam, here it will be over-reinforced section and dimensions have to be changed. But in this case, as we are designing a doubly reinforced beam, we can go ahead and design the section as doubly reinforced beam. Now see the conclusion what I have written. Mu is greater than Mu limit. The section is to be designed as doubly reinforced beam. If Mu was less than Mu limit, the section was singly reinforced. But as we are doing the experiment on doubly reinforced beam itself, okay, we will get the conclusion Mu greater than Mu limit, and the section needs to be designed as a doubly reinforced section. So up to here, the things are quite similar and quite easy. Nothing different we have done than experiment number 1. So what happens in examination is, once you prepare singly reinforced beam, half of the doubly reinforced beam experiment is covered. Okay, half of the doubly reinforced beam experiment is covered. Now what is a doubly reinforced beam? It is that structural beam in which we have reinforcement in tension region as well as the compression region. In the singly reinforced beam, we designed only AST, whereas in the doubly reinforced beam, we have to design AST as well as we have to design ASC. Okay, AST as well as ASC are required. So we all know that steel is always good in tension. But now, in this case, in step number 11, we will have to use the steel for compression. So in that case, maximum permissible stress in compression, let us adopt 0.87 Fy, which is the maximum value which we can use. So while solving, we refer the SP16 code book and try to get the value of FSC, do iterations. So in Excel sheet, we are avoiding that. Directly in Excel formula, we will adopt FSC, that is permissible stress and compression of the steel, as 0.87 times of Fy. Directly we will take this. So 0.87 multiplied by Fy. Here the formula is given again. Okay, no need to worry. 0.87 multiplied by D13. What is there in the D13 cell? D13 cell stands for grade of steel. So automatically, if you make it 250, 0.87 will be multiplied by 250 and this value will change. So this is how you will be getting maximum permissible stress in compression region, 0.87 Fy. So this step is quite simple. Now further we'll refer IS 456 page number 96. So here I have IS 456 page number 96 for you all. So in IS 456 page number 96, this gives you the design of beam. All the formulas required can be adopted from here directly. So we'll be using this formula to find AST. Okay, here D and D will get cancelled. Okay, so here this D and this D will get cancelled, and we'll modify this formula and use that formula to find AST directly. Okay, we'll modify the formula and use it to find AST directly. Then further we have here the formulas. Okay, this formula we'll be using to find ASC, that is area of compression steel. Okay, this formula will be using this cross multiply, send to the denominator the other two terms, and here this formula we'll use to find ASC. Now FSC actually we can find using this relationship, 0.0035 XU max minus D dash upon XU max. But to avoid complications, what we'll do is maximum permissible is how much? 0.87 Fy. So we'll use that maximum permissible as FSC. For FSC, we'll not use this formula. We'll use the direct formula for FSC as 0.87 Fy. We'll avoid using this formula. We'll use the direct formula. So from this formula, that is 6.11A, we'll get AST value. Then from this formula, we'll be getting ASC value. And one more component of AST comes in as it's a doubly reinforced beam. Now that you have to remember. So there is one more formula which I have highlighted, AST2. So AST here in case of doubly reinforced beam will be made up of two parts, AST1 and AST2. So here what is AST1? AST1 is the area of tension reinforcement for singly reinforced section. If the example just was singly reinforced section, what formula we have to use? That is only for AST1, which is there in the (6.11a). So from this formula, what you get AST, we have to refer it as AST1 in the doubly reinforced beam, and formula for AST2 is given. So this page will be permitted in the exam. You can get your IS 456 code books. So this formulas also you can take it from here only, not an issue. So the formulas you can take directly from this code book itself. So now these code book formulas from page number 19, let us adopt or incorporate in our Excel sheet. So now we'll be using the page number 96 formulas in our Excel sheet to get the area of compression reinforcement and area of tension reinforcement. So area of compression reinforcement, what was the formula? Here the formula is written. So once you refer the PDF sheet, things will be easy. ASC is equal to mu minus mu limit divided by FSC into D minus D dash. Okay, from where I have got the formula? From page number 96. Now what I have to do here is connect the things. Okay, what I have to do is, where is mu? Where is mu limit? Just put it in the form of the formula and you will get the required answer. Once you put the things in the required form, you'll get the required answer very much easily. That's the beauty of using Excel sheets. It makes your things very, very, very simple and very light. So how will I get this as mu minus mu limit? That is, here I have written again D3 minus D20 divided by D22. Now D22 should be FSC. Now let's see here D22. So this cell is D22, which stands for FSC value. So connecting that, I get ASC. So area of compression reinforcement, what I require is 270.02 mm square. Okay, I require 270.02 mm square of compression reinforcement. Next, the area of tension steel required, AST1 formula we have seen, page number 96, 0.36 FCKB XU limit divided by 0.87 FY. Using the direct formula, AST1 is that reinforcement which takes care of the beam as a singly reinforced section. It is not taking the care of the extra moment. So here this is termed as AST1. So we get AST1 as 924. Now these calculations you can verify using the calculator. But if you have to use calculator, then there is no need of Excel sheets. Okay, it's waste of learning. So your Excel should be so perfect that you need not verify it using the calculator. Next, area of tension steel, AST2. Now this is that extra steel which we require for the extra bending moment, which is above mu. So again, use the formula from the code book. See here, the code book formula is there. AST2 is equal to ASC FSC divided by 0.87 FY. So I'll get the value of AST2. I'll get the value of AST2. Therefore, total reinforcement AST is equal to AST1 plus AST2. Again, it is written here. It is very much clear. Need not worry. And if you want, formula is also given here. Okay, so I have tried to make the things as clear as possible. Once you sit back with this sheet, you can refer everything. Okay, so only I have sent the Excel as well as PDF sheets in the group. So this is totally addition of this both. We get 1194.68 as the area of tension reinforcement required. So main thing now is the steel and the compression steel. These both we have to provide, so that we'll get the required solution of this experiment. We wanted to find reinforcement in tension region as well as compression region. Now same, the formulas which we have used, number of bars required in tension region is equal to AST, that is this AST value 11946 divided by area of reinforcement bar selected. Now for AST, we have selected 20 mm diameter bar. So when you put area of steel required, that is 1194.68 divided by area of 120 mm diameter bar and round up. Why we have to round up is we should get the whole number. Okay, we should get the whole number. So we have to round up. So round up formula goes like this. First comes round up, at the end of the bracket comes comma 0, means anything above 0 goes to the next number. If you remove that, you'll get the answer 3 point something. So in that way, we cannot provide the reinforcement bars. This was explained to you all in the last class. And once you work out yourself on the Excel sheet, you'll get a better idea. So we got 4 bars of 20 mm diameter. So similarly, what we have done, in the compression region, we had to provide only 270 mm of steel and we had selected 16 mm bar. So using the formula, we got 2 number of bars required. So this is what is the answer which we were looking out for. So these experiments are quite easy Excel sheets. Only it is you have to play with the formulas and connect them properly so that you get the required solutions.